Previously, we've defined work as being equal to the force applied in the direction of motion multiplied by the displacement. In the last video, we also defined work as being the change in the kinetic energy. Consider a group of joggers out for their morning run. They're doing work by pushing against the friction between their feet and the ground to move them forward. In the process, they lose energy and get tired. So here's a question. If one of the joggers decided to run ahead of the pack and starts to sprint, will he get tired more quickly or the same as the others who are jogging? Our experience tells us that if you do things fast, you get tired more quickly. So the rate at which you do work has an impact. We call this power. So power is defined as a rate of work done or the amount of energy change per unit time. Since power is defined as work divided by time, then the unit for power is joules per second. But we also give it the unit of the watt, where 1 watt is equal to 1 joule per second. The unit of the watt is named after famous Scottish engineer and inventor James Watt. Watt was famous for, amongst many things, reinventing the steam engine that started the Industrial Revolution. Watt was able to describe how energy can be transformed from one form, such as heat, to another form, such as mechanical work. The unit of power is named after him in recognition of this. So power is defined as the work done divided by the time taken. But work is defined as a force multiplied by the displacement. And we know that displacement divided by time is equal to velocity. So power can also be defined as a product of force and velocity. Let's go back to our Lamborghini Huracan. The car has a maximum power output of 449 kilowatts from its 5.2-litre V10 engine. This means that its engine produces 449,000 joules of energy every second. This is roughly equivalent to consuming 2 Mars bars every second. Let's consider this example where you're a building services engineer installing a new elevator in an office block. The elevator has a mass of 1 ton and can carry a maximum load of 800 kilograms. When it's moving at its maximum speed of 3 meters per second, it experiences a constant frictional force of 400 newtons. Your task is to select a motor for the elevator with enough power to pull the elevator with its maximum load at its maximum speed. To solve this problem, we need to consider the rate of work that needs to be done. The motor must pull the elevator up at a rate of 3 meters per second, and the force that it applies to the elevator must be able to overcome the force of gravity wanting to pull it down, as well as friction. So let's start with the definition of power being the rate of work done, or the product of force and velocity. Given that we have information about the forces acting on it, we'll use the second definition. When the elevator is moving at its maximum speed, it is moving at a constant speed of 3 meters per second. Then the net force is 0 since there is no net acceleration. So the force applied by the elevator must be equal to the force of gravity plus the force due to friction. Gravity acts on both the elevator itself and its load. So the total mass in this equation is the mass of the elevator, which is 1 ton or 1,000 kilograms, and the maximum mass of the carrying capacity, which is 800 kilograms. So the total mass is 1,800 kilograms. Since the acceleration due to gravity is 9.8 meters per second squared, and the frictional force is 400 newtons, then the total force needed is 18 kilonewtons, or 1.8 by 10 to the 4 newtons. So what is the power needed to pull the elevator up at a speed of 3 meters per second while carrying its maximum load? So power is force times velocity, which is 1.8 by 10 to the 4 newtons multiplied by 3 meters per second. This gives us a power of 54 kilowatts. So the motor needs to produce at least 54 kilowatts of power in order to pull the elevator up at its speed at 3 meters per second while carrying its maximum load. In summary, power is defined as the rate of energy used or the rate of work done over time. It is also equal to the product of force and velocity and has units of joules per second or watts. Given that both work and time are scalar quantities, then power must also be a scalar quantity.